Okay, this is our last little video on this related rates section. I've got 3 problems up right here. You can give them a try. So pause the video, give them a try, and see how you make out. And then start the video back up, and I'll work through the solutions for you. So let's go with the first question. Ship A is 50 kilometers north of Hawaii and sailing towards it south at 10 kilometers an hour. At the same time, ship B leaves Hawaii and sails east at 15 kilometers an hour. How fast is the distance between the ships changing 2 hours later? Okay. In this picture, we're going to start with a diagram. All right, we'll let this represent Hawaii. We have a ship sailing south towards it, and at the same time, we have a ship leaving Hawaii and heading east. They want to know the rate at which the distance between the 2 ships is changing. Now, in this diagram, all 3 of these distances are changing. It's unlike the ladder question. It's similar to the ladder question in the sense that we drew a right triangle. But I think you'd agree that this distance right here is changing. This distance is changing, okay? As ship B leaves, that's going to increase. As ship A sails towards Hawaii, that's going to decrease. All right, and this distance is also changing. We said that if something's changing, we assign it a variable. Now, because they're talking about ship A and ship B, I'm going to call this A, this B, and for that matter, this will be C. Okay, they do tell me the rates. You don't have to use A, B, and C. You could use X, Y, and Z if you want. I think it's probably most common to use A, B, and C. And we'll go dC over dt. Now, if we keep reading, if we look here, I think you'll see that ship A is traveling at 10 kilometers an hour. Now, let's think about that for a second. Is that distance increasing or decreasing? The answer is decreasing, all right? The distance between ship A, where it started, 50 kilometers, and 2 hours later, okay, it's going to be gaining or shortening the distance between itself and Hawaii. So this would be a negative. Ship B leaves and goes at 15 kilometers an hour. Now, let's think about that in terms of increasing or decreasing. Leaving Hawaii, it's obviously getting further away. Okay, it's traveling away from Hawaii. The distance is increasing at 15 kilometers an hour. It wants to know how fast is the distance between the ships changing, so it wants to know this value. So if it tells us dA over dt and dB over dt, I'll just kind of highlight those things. What formula could I use that would relate these quantities? Well, the answer is the same as the ladder question. I can use a squared plus b squared equals c squared. Now in the ladder question, the ladder was a constant, so I filled in the value there. Remember, if something's changing, you can't fill it in until after you differentiate with respect to time. So I'm going to do that. Let's go with, that's all right. Capitals, I'm not going to get too bent out of shape on me, are you? Two times C times dC over dt. Okay, we said I'm looking for this. I have dA over dt, and I have dB over dt. They also give me enough information to figure out the missing sides. So I can find A, B, and C. Okay, well, let's think about this. This B value is pretty straightforward, pretty easy. All right, it's traveling at 15 kilometers an hour, and it travels for 2 hours. We've got to use the time here. Well, how far would ship B travel in 2 hours? 30 kilometers. Okay? So B is 30 kilometers. I took 15 kilometers an hour and multiplied it by 2. So by that logic, I should take 10 kilometers an hour and multiply it by 2 and get 20 kilometers for A, correct? Wrong. Why is that wrong? Well, think about it. Ship A was 50 kilometers north. It definitely traveled 20 kilometers. What's the distance that remains? Okay, this would actually be 30 kilometers as well. Just make a little note. I took 50 kilometers. That's what I started. That was the distance I was away from Hawaii in the beginning. I traveled 20 kilometers. That leaves 30. Now I can find C. All right, A squared plus B squared equals C squared. To find C, I'll just fill in 30. And that'll give me 900 plus 900 equals C squared, or 1800 equals C squared. And that would give me, take the square root of 1800. That would look like this, 900 times 2. C, I'll just leave it as a radical for now, pull that out. 30 root 2, that's my C value. So I have 30 for A, 30 for B, and 30 root 2 for C. So I can fill those in. I know that value, that was negative 10. I know this value, that was positive 15. And I'm looking for dc over dt. So this would be, my A value was 30. My B value was 30. That's because ship A is now 30 kilometers north of Hawaii. Ship B is now 30 kilometers east of Hawaii. And that distance would actually be 30 root 2. I know dA over dt, that was a negative 10. And I know dB over dt, that was a positive 15. Again, negative because that distance is decreasing, positive because that distance is increasing. And when I solve, this would give me negative 600. 30 and 30, that's 900. And that is 60 root 2 dc over dt. 300 on the left. I'm going to divide both sides by 60 root 2. 300 over 60 root 2 equals dc over dt. Reduce that. 300 divided by 60 would be 5. So 5 over root 2 has an exact value. What would the units on that be? The units on this would be the same as the units on this and the units on this. So kilometers an hour in this question. As an approximate value, 5 divided by the square root of 2. What is that? 3.535. We'll say 3.54 kilometers per hour is equal to dc over dt. Either or acceptable. So there is the solution for the first one. Okay. On to the next one. This one's a water tank, and it's built in the shape of a circular cone. So this is important. All right. Draw a little picture. Here's what a cone looks like. It's kind of like a party hat or one of those little cups you get at the water cooler. All right. It's got a height of 5 and a diameter of 6. It says water is being pumped into the tank at a rate of 1.6 cubic meters per minute. Find the rate at which the water level is rising when the water is 2 meters deep. All right. Let's look at this for a second. What did they tell us right here? That is dV over dt. How do I know it's dV? Cubic meters. And it's per minute, so it's definitely with respect to time. They also give me a bunch of other information. All right? They tell me that the height is 5 meters. That's what the cone would be. That's how high it is. And it's got a diameter of 6. Okay, let's use the radius. We'll use the radius in this question. So that's what I know, and they do tell me that they want me to find the rate at which the water level is rising. So basically what's happening is water is being pumped into this, and the water level starts to rise, and they want me to figure out the rate at which it's rising when it has a height of 2 meters. Okay, now think of this. The height's going to be changing, correct, as it fills until it's at its maximum height of 5. But we're asked to find the rate at which the water level is rising, so dH over dt, when the height is 2 meters. We got to find a formula that relates the volume, okay, of a cylinder, a cone. The volume of a cone looks like this: 1/3 pi r squared h. Now here's the problem. They want me to find dH over dt. The rate at which the water level is rising. Problem is I got R and H in this. Okay, they didn't tell me, like, if I'd solved this, or if I differentiated this with respect to time, I'd have a dV over dt, a dR over dt, and a dH over dt. Well, they only tell me this one, and they ask me to solve for this one. If they don't give me that, dR over dt, then I got to do something to this. I got to express this formula with a single variable. I'm going to express it in terms of H only. So that means I need to replace the R with something. Okay, well, let's use something we talked about in a previous question, similar triangles. We can achieve that. All right, let's look at the large triangle. All right, that would be 3, that would be 5. Think of the water level rising. Right, this represents the radius, this represents the height. So I can say that R over H is equal to 3 over 5. I'll set up a proportion. R over H is 3 over 5. R and H, those are changing, right? Because the water level rises. As water's being pumped in, this is going to, not a 5. This height is going to change, and the radius is going to get bigger as it kind of moves its way up. So those are changing. That's why I used R and H variables, and I used R for the radius and H for the height. Now with some manipulation, I can rearrange this so that it says 5R equals 3H, and I want to put it in the form R equals. So I'm going to divide both sides by 5. The reason I want to put it in the form R equals is because I want to maintain, or I want to keep the H in the equation. All right, now I can replace this R right here with this expression down here, 3/5 H. And again, I wanted to keep the H in this formula here because I have to solve for dH over dt. When I square this, I'll get 1/3 pi, that would be 9h squared over 25 times h. So 3h times 3h would give me 9h squared. 5 times 5 would give me 25. Let's see, clean this up. So that's going to be 1 times pi times 3, so 3 pi, h squared times h would be h cubed, and that's a 1 times a 25. So this is what I have. Now, this is good, all right? I know dv over dt, so when I differentiate this with respect to time, I'll get a dv over dt, and I only have one variable now. I'm asked to solve for dh over dt, so we're good to go. All right, remember, I'm not going to fill this value in when the water's 2 meters deep, like that's my h value. I can't fill that in because we said that value was changing. Look, we slapped an h on it, the variable h, because we know as water comes in, the height is going to rise. So I can't fill that 2 in until after I differentiate with respect to time. Now, this is going to be 3/25 pi, that's a constant, times the derivative of h cubed with respect to time. So that would be 3h squared times dh over dt. And this is going to give me dv over dt. 3 times 3 is 9 pi h squared dh over dt over 25. Now I'll fill in what I know. I know this was 1.6. All right, dv over dt. Not making that up, it was given. And I know that this was 2. If I scroll back up here, h was 2. So I'm going to have 9/25 pi times 2 squared, which is 4. And I should be able to solve for dh over dt. Now, 1.6. So without a calculator, if you're ever asked to do these without a calculator, I won't, but they might at the next level. Okay, that's like 16 over 10, or 8 over 5 if I reduce that. Okay, so I've got 8/5 equal to, this is going to be 9 times 4, 2 squared is 4, times 9 would give me 36, times pi is 36 pi, over 25, times dh over dt. Again, you don't have to do this without your calculator. You can figure out what 36 pi divided by 25 is and leave that as 1.6, and then just divide both sides by whatever this equals. But just remember, if I want to get rid of that 36 pi over 25, divide both sides by that. Remember, when you divide by 36 pi over 25, it's like multiplying by 25 over 36 pi. Well, this, 25 divided by 5 is 5. That would reduce. Okay. They're both divisible by 4, so that would give me a 2. And this would give me a 9 pi. Okay. So when I multiply 5 by 2, I've got 10. 9 pi by 1, I've got 9 pi. And that's my dH over dt. Now let's think about this for a second. H would be measured in linear units, the height. Okay, so it'd be meters if it were just height, but since it's dH over dt, it's got to be meters per minute. Not min. Has an approximate value, 10 divided by 9 pi. 10 divided by 9 pi gives me 0.3537 meters per minute. Okay, so there's that one completed. That one had a little catch to it. All right, I had to express this with in terms of h only, v in terms of h only, because they didn't give me enough information with the rate at which the radius was changing or anything like that. And I just did that using similar triangles. The radius and height of the water being pumped in is constantly changing, so r over h. to a maximum of 5 meters high and a radius of 3 meters. That's the capacity, we'll say, of the tank. Okay. One last question. So trig one, so this will involve a trig function. And I'll show you kind of a way I like to do it. You can solve it using a trig function, but I like to use an inverse trig function actually, because it's asking for the rate at which the angle between the string is decreasing or changing. So kite 40 meters above the ground. So here's my kite. It's 40 meters above the ground. And it moves horizontally at a rate of 3 meters per second. So it's going this way at 3 meters per second. What rate is the angle between the string and the horizontal decreasing when 80 meters of string is let out? Okay, so let's think about this. They're telling us the kite is always 40 meters above the ground. So that is a constant. All right, I'll assign a variable to it, I guess. It's 40 meters. Okay, why it's not changing. What is changing are the x value and we'll say the z value. They do tell me, however, they want me to find the rate at which this angle down here is decreasing as more and more string gets let out. So think about what's going to happen to that. All right, if this kite moves this way, z's definitely growing. Okay, x is getting bigger. Y is constantly staying 40 meters. That angle is decreasing. That's kind of the setup of this question. All right. So that rate they give me, it's the horizontal rate. It's the rate at which the horizontal distance is changing. So dx over dt is 3 meters per second. We want to find d theta over dt. All right. Now, come up with a relationship that would relate these two quantities. Okay, I want to use this x value because that they give me dx over dt. So I've got theta here, I've got the opposite side, and I want to use the adjacent side. Okay, why do I want to use the adjacent side? Look at the information given, dx over dt. I need to put that into the derivative. So in order to get a dx over dt, I have to have an x in my original equation. So if I have the opposite and adjacent sides, I can use tangent. All right, it's 40. That is a constant. It's not going to change, so I can pump that in. I don't have to put y. And I'll put x here. Now, you could solve this right like this. Do the derivative of tangent theta, so you get secant squared theta d theta over dt. Do the derivative of this. I prefer to rewrite the function like this. Okay, if tangent theta equals 40 over x, theta is going to equal the inverse tangent of 40 over x. And this, okay, is a pretty easy derivative. So now I can go d theta over dt equals, remember the rule for inverse tangent, it's 1 over 1 plus u squared, so my u value would be 40 over x, I'm going to square that, times du, so the derivative of 40 over x, that's like this. So that would be negative 40x to the negative 2. That would give me negative 40 over x squared times, don't forget your dx over dt. You're differentiating with respect to time. Now I can solve for d theta over dt. All right. This would give me 1 plus 1 over 40 squared is 1600 over x squared minus 40 over x squared. Sorry, that's times negative 40 over x squared. I'll do it like this. Times dx over dt. All right, now in order to solve this, I need to find x. Well, I can find x when z is equal to, how much string was let out? Okay, when z equals 80, when there's that much string left out, this is what my triangle would look like, 80. Remember, the height is always 40. So I could find x, no problem. How? Pythagoras. Pythagorean theorem. So x squared plus y squared equals z squared. I'm going to go x squared plus 40 squared equals 80 squared. X squared is going to equal, that's 6,400. That's 1,600. X squared is going to equal 4,800. Now, a lot of times people are going to, like, I shouldn't say a lot of times, most times, we're inclined to figure out what x is by taking the square root of both sides. I just want to show you a little trick. Okay, look at it. We've got x squared in our equation. It doesn't say x anywhere. So there's no sense taking the square root of it when you're just going to have to turn around and square it. So I can just fill those x squareds with 4,800s and work this out. So this would be 1,600 over 4,800. This is going to be negative 40 over 4,800. And this is going to be dx over dt. That's what I'm looking for. So, sorry, no, that's given. Dx over dt was given. That was the 3 meters. Okay, if you scroll back up, dx over dt, here it is at 3 meters per second. And I know x squared is 4,800. So when I fill this in, it looks kind of greasy, but it's actually not too bad at all. Because I can reduce this to 1/3. 16 over 48 is 1/3. So I've got, in this first bracket, 1 divided by 1 plus 1/3. This is going to reduce to negative 4, so that'd be 48 divided by 4, 16, 160. 160, let me check that, 4. Yeah, we're good there. No, we're not good there. Maybe 2 over 240. 120 is what I should have. And that's a 3. Okay, so 16 over 48 is 1/3. 4 over 480 is 1 over 120. That's a 3. So this becomes the following. 1 divided by, well, that's 3/3 plus 1/3, that's 4/3. 1 divided by 4/3 is 3/4. This is negative 1 over 120, and this is 3. So I've got d theta over dt equals negative 9 over 480. And I can divide both of those by 3. That gives me negative 3 over 160. And slap some units on this one. Now the units in this one are, we're actually finding the rate at which this angle is decreasing. Well, that angle theta would be measured in radians, okay? And Remember, it's d theta over dt, so the dt, the time, would have to match up with the time in this, which is seconds. And if you convert that to a decimal, negative 3 over 160, negative 0.01875 rads per second. Okay, full screen that, check it out. That's one involving trig. So now I should have a good handle on these related rate problems. We've gone through several examples. You can use the rest of the time to kind of practice your craft. All right, if you have any questions, feel free to message in Teams or just ask in class.